All right, hello and welcome. In this video, we're going to look at how to calculate the impedance and express it in polar form. So we have an RLC circuit here, and that means that we have a linear component, that resistor, and we have two nonlinear components, our XL and our XC. And they've given us XL and XC and not the henries and the capacitance values. So that means that they've already calculated a piece of this for us. So we just need to plug it into our Z equation. And our Z equation says that Z is equal to the square root of our linear component, we'll call that R squared, plus our nonlinear components, we'll call that X total. And that's also known as the net reactance. And so X total, or the net reactance, is equal to our XL minus our XC. And so we can have that plugged in there. We also want to square that after that in our top equation, right? Because this is our triangle equations. And so when we solve for that, we'll just plug in our XL minus XC in for our X total and square it. And that's going to give us our magnitude of Z. And so we can solve for that. We can say Z is equal to, we'll type that into our Desmos over here, the square root of R, which is 120. And we'll square that and add it to our X total. So I'm going to put a parenthesis here and we'll add up our X total. We'll say it's XL, 165, minus our XC, 52. We'll close that parenthesis there and square it. And that is our Z. So we'll say Z is equal to 164.8, so we can round that up to 165. And that is in ohms, right? That's only our magnitude. So this ohm right here doesn't actually go after the 165, right? So we're going to leave that off for now, and we're going to place it at the end of our polar form, which means that we need to find our next angle. We need to get after the theta for this circuit. So our theta is equal to our inverse tangent equation, just like our triangle equations when we were doing the rectangular to polar form conversions. And so we'll pull that out. We'll say that that was our tangent to the -1 of our nonlinear component, X total. That's our divided by our linear component, which is our resistor, right? That's going to be resistor total also. But right now we only have one resistor. So we can plug that in and say that theta, this is the angle of our magnitude for our total impedance, is equal to tan to the -1, and then we'll put in what we know that is. So that's going to be our XL minus XC. Sometimes that becomes negative. That's going to give us a negative phase angle, right? On the bottom, we want to put our resistor, and that's 120, right? So 120. And we'll plug that in. We get a degrees out of that. So make sure your calculator is in degrees and not in radians, right? That's going to give you a different value. So in the function tab, we'll find the inverse tangent button, pull that out. And we'll say that we have XL minus XC. So we'll open an extra parenthesis here and say XL was our 165 minus our XC of 52. And we'll close that off and divide it by our resistor value of 120. And that gives us 43, we'll round that up, 43.3. So 43.3, and that's in degrees. And remember, if your calculator's not in degrees, you're going to get a really, really, really small number, right? A point decimal range. And so we don't want that, right? So make sure you're in degrees and not radians for that angle. Whenever you're using tangent, sine, cosine, all that kind of stuff needs to be in degrees. So we have a final answer now. We have Z is equal to 165. That's our magnitude at an angle of 43.3 degrees. That's our angle there that it's at. And then our value is in ohms. So we'll put our ohms value at the end. So kilo ohms, ohms, amps, all that goes at the very, very end of your full polar number. All right, let us know if you have any questions.